is what is called the most common oxidation number. Now that's a highfalutin word that's on the handout that I gave you. The most common oxidation number. Okay? Now remember, every atom up here wants to have how many electrons? 8. That's the octet rule. That's the magic number. So, if you were lithium, as an example, what could you do to have, oh, I don't want to use lithium. What if you're sodium? What could you do to be like your nearest noble gas, or to be like a noble gas? All right. So, if you are sodium, you could give away 1 electron. That is if you are sodium. Okay? And if you give away 1 electron, what would you be like? You would be like neon. Does everybody follow that? Now, what charge would you have if you give away an electron? Positive 1. Now, let's think about this. This is always counterintuitive because ever since the 3rd grade, a plus sign to you means add. But not for atoms. You see inside this nucleus are positive charge called protons. Now, sodium just happens to have 11 protons. And if there were 11 electrons about this orbiting in some fashion, what would be the charge of that atom? 11 electrons, 11 protons. What's the charge there? 0, right? Every positive and every negative cancel each other out. Okay, but if sodium lost the electron, that's what you said you wanted it to do. It's now got 10 electrons, not 11. Now what's the net charge there? Positive, right? Because 10 of these electrons are canceled with how many of these protons? 10. How many's left over? 1 positive charge. So when you lose an electron in chemistry, there's a positive charge. Now, what else could sodium do to be like its noble gas? It could gain how many electrons? 7. That would make it a what? An N? What charge is that? Negative 7. And that way it would be like, instead of neon, it would be like what? Argon? Now, energetically, what do you think it's probably going to do? Lose 1 or try to take in 7? Lose 1, right? All right, and that's in fact what this column does. Plus 1 all the way down is the most common oxidation state. Now what does that mean? That means if it gets near something, instead of reaching out there and grabbing the electron off of her red top, what it will do is it will just force an electron in there. Now that's not necessarily a good thing either, right? Because, you know, not enough electrons is a bad thing, and then too much electrons is also a bad thing. But that's how sodium does its reacting. If it gets near you, it will just throw one down your throat and make you take it. All right? That's where this plus 1 comes from. Does that make sense? Okay. What happens here? What's its options? Let's just randomly take magnesium. It could gain how many electrons to be like argon? 6. Or it could do what? Lose 2 to be like neon. What's your bet? There you go. What charge is this going to be? Plus 2. Do you guys see that? Because if you're losing electrons, it's positive. Okay, let's look at aluminum. We always skip transition metals for now, and I'll show you in just a moment after we talk about these simple examples why. There's a whole class I took one time called D-block chemistry. That is the chemistry of the peach, and that was it. All right. Why am I telling you that? Well, the chemistry inside of transition metals is quite complicated. It's elaborate, it's prolific, meaning there's lots and lots of information there, and it is in a lot of cases unpredictable. Okay, so let's look here on this main group. What's going to happen here with aluminum as an example? Is it going to lose 3 or is it going to gain 5? It's going to lose 3. That's more energetic. That's easier for it to do. So what charge would these all be then? Plus 3 as the most common oxidation number. Listen to me. Did I say that these numbers up here, as we working across, are the only thing that's going to happen, period, in life? That's it. No, I said what? It's the most common scenario to happen. Look at carbon. Is it going to lose 4 or gain 4? Either way. Either way. Go both ways. Okay. What about nitrogen? Is it going to lose 3? Lose 5 or gain 3? Gain 3. What charge does this need to be? Most common. Most common. What here? -2. -1. And what's down through here? 0. Ain't nothing wants to happen there. These are called the oxidation numbers. This is in reference to how many electrons that they will gain from something else, or they will lose to something else. Do you see how these things here, the nonmetal side, they suck electrons from things? Does that make sense to you? Or these electrons over here, they're generally given to something else. All right. What are you doing back there? Could you imagine if we were like talking about the ghost of chemistry past or something and that happened? Do you believe in ghosts? Do you guys believe in ghosts? You do? Who believes in ghosts around here? Anybody? One person? Can't believe only one person in this room believes in ghosts. All right, let's look at this. Okay. Let's take boron. Do you see that number written up there? Let me cut the lights so the other people can see this. What's written up there? A 3. Well, that's no new news, right? What's written there? 3. What's written there? 3. There's also a 1 written there. All right. Now, let's look at the other side of the periodic table. Nitrogen is what? -3. I don't know if you guys can see this detail or not. All right. But which one is bolded there? All right, the -3. That means it is the most common situation to happen. However, a +3, a +5, a +4, and a +2 have been discovered, noted, and are routinely used. How about oxygen? -2. But there's also a what there? Which one's the most common? -2, just like I told you. Okay. Do you guys see that? Yes, no, maybe? Yeah? Okay, now fluorine over here, notice that it only has a -1. But look at chlorine. It's got a bunch. But what's the most common for chlorine? -1, just like I told you. All right. Now you look at transition metals over here, right? I mean, this stuff can get carried away. Look at osmium. God knows. There's a +4, an osmium-8, an osmium-6, an osmium-3, and an osmium-2. Rhenium, 7, 6, 5, 4, 3, and 2. So how do you study that? Well, you have to take whole classes on it. You know, I mean, how do you get into that? I mean, it's just kind of complicated. All right, are we good? Okay, then let's see how this is going to work. Now, here's what I want you to remember as far as these net